CS Aizawl more value. So currently do like it more. Để nó sản phẩm stick chỗ đặt mấy nhá mò làm được có sủi sticking nha.
Hello, is my screen visible?
Yes,
Yes,
sir.
sir, it's visible.
I can hear you.
Okay. And screen also you can see.
Yes, sir. Yes, we can see it, sir.
I need to go to the CS I can more.
Okay, I'm ready then. You can start now.
Okay. Sir is ready. Shall we start the webinar? Okay. We shall start the webinar. Good evening, everyone. Respected Principal Professor J.B. Nunsunga, my esteemed colleagues, fellow teachers from other institutions, and my dear students. Thank you for joining us for tonight's webinar. My name is Dr. Larinkini Patsual, Assistant Professor, Department of Economics, Govt J. Thankima College. The topic for tonight's webinar is modeling relation variables, some new development, to be presented by Dr. S.K. Jha, Associate Professor, Department of Statistics, Northeastern Hill University. I welcome you, sir. And just a little housekeeping before we started. I would like to firstly seek your cooperation in completing the seminar. Kindly mute your speakers to avoid any interruption. And if you have any questions during the presentation, please type them into the question box, or otherwise we will have time for vocal questions at the end of the lecture. We would also like you to know that tonight's webinar is being recorded. And now, without further ado, we will turn our time over to Dr. S.K. Jha, our presenter today. And Dr. S.K. Jha is currently an associate professor in the Department of Statistics, Northeastern Hill University. He has a PhD in statistics and has also cleared the National Educational Test by UGC in 1986. His area of specialization is probability distribution, statistical models, and spatial statistics. Dr. S.K. Jha is an expert in his field with 25 years of experience, and he has taken up numerous projects and surveys which are all very enticing and groundbreaking, and also wrote and published a handful of research articles such as a skew, normal spatial simultaneous autoregressive model and its implementation, and assessing burden of infant mortality on socioeconomic classes in northeastern India, to name a few. Dr. S.K. Jha has also delivered a successful series of public lectures and paper presentations. And now we shall hand over our session to Dr. S.K. Jha, our esteemed resource person for the night. Sir, Dr. Sir, the floor is yours.
Okay, thank you very much for such a nice introduction. And only one thing I'd like to know from you before I start. So the participants are all either working in statistics or econometrics?
Yes, sir. The participants have a background in statistics.
They have statistics background.
Okay, the students as well as the teachers from other institutions.
That's good. Very good. Very good.
Yes, sir.
Okay, then this is my time is 1 hour, isn't it?
Sir, there is no specific timeline. You can take as much as time as you want.
Okay, okay. Thank you. Thank you. So my screen is visible, and now I'm going to start it. So today I'll be speaking on modeling relationship between variables, some new developments. I'll basically concentrate on what developments has taken place during the last 50 years, because many things has been developed, and those are yet to come in, say, even master's course. We are using it in research, but research from our area, very less tools have been used. So just first try to understand what is this relationship between variables. Actually, though the name I'm putting as relationship between variables, but here primarily we'll be discussing the regression type of models. And you were aware that the regression type of models are the models which are being used the most in research, say research methodology or research applications. These models have been or are being used the most. So most of the developments has taken place in this. Now, just a few terminology. Otherwise, we know it by different names. So in research methodology, we have variables, more than one variable. One type of variable we call as response, in which we are interested in modeling. Response variables are also known in the name of outcome variables or dependent variable. This is the dependent variable is the terminology I think used in economics or econometrics most often. Then there are a set of explanatory variables. These variables are also called predictor or independent variables, and they are assumed to be least interacting among themselves, but they have effect on response. And usually we are interested in measuring the effects of explanatory variables on the response variable. Well, before we proceed further, I'll like to bring to your attention that one very basic thing which usually we miss out in some classes and while thinking or reading this regression also, those are the measurement scales on which the variables are being measured, because our statistical tools or techniques, they depend upon which type of measurement scale the variables has been measured. So basically there can be more, but the measurement scales are nominal, ordinal, and continuous. I'll just put in continuous. There are two types of scales, interval and ratio. So nominal and ordinal. Nominal means those variables which can be which have different categories or different labels, which is only for the namesake. Like you see gender. Gender, if you are putting gender, if you are measuring as a variable on the objects or subjects, usually subjects, then it has two categories, male and female. Like so in respect to some colors or this, so normally, or state of domicile. So nominal and ordinal are those variables which can be arranged, where we have some sense of large and small this level values. And then continuous, like most of the measurements that we are interested in, like weight, length, area, volume, all these are continuous measures which are usually real numbers. And here we have two different types of continuous variables, interval and ratio. Interval variables like say Celsius thermometer scale when you are measuring, or Fahrenheit thermometer scale, or intelligent quotient. Now these are the scales where 0 is not meaningful, but the interval has meaning. Has a meaning, it is constant and it can be compared. And ratio scale is an interval scale with meaningful 0. Means 0 means absence of that. So IQ 0 doesn't mean that the person is missing IQ, or the Celsius scale, say 0 degrees Celsius, doesn't mean that the temperature is absent, but Kelvin scale is a ratio scale. So these are the differences. Now, why I'm talking much on this is that the statistical procedures that we are going to see will depend upon the measurement scale. The regression analysis, what you have read, most of you in graduation or post-graduation, what we are giving, are from continuous scale measures. And now recently, we have also developed regression type of analysis in case of nominal and ordinal variables. That I'll be discussing a little more in our next slides. Now, the point that I was trying to make is that depending upon the type of or measurement scale of the variable, we have methods These methods you must be familiar with. I'm just revising these things to you, or making you to again revise it for this talk. When your response is continuous, response means again the dependent variable, and your explanatory variables are binary. Usually the statistical methods we can use is t-test. I think most of you are familiar t-test, z-test kind of thing. If your response is continuous and your explanatory variables are nominal scale measures with more than 2 categories, then what we can, statistical method that can be used is analysis of variance. I think analysis of variance also you must be familiar. If we have response continuous and explanatory ordinal, then again analysis of variance. Both continuous, then we have multiple regression methods. Then other methods will not be using, we'll be using multiple regression methods. If response is continuous and explanatory variable is nominal, or nominal and continuous both, then again analysis of covariance methods are used. Continuous response and with explanatory variable categorical and continuous, then multiple regression again. Now, what is categorical? The scale or the variables which are either ordinal or nominal. So both together can be called by this name, categorical variables. So then this method may be used. So some more. Now, if your response is binary and your explanatory variable is categorical, then logistic regression or contingency table methods, these are the methods that has been used. Now, these are new methods. It's not very old. Binary response with explanatory variable continuous, method logistic regression. Binary variable, explanatory variable categorical or continuous, then again logistic regression. I'll just try to little bit more elaborate this thing. Binary. Now, suppose if you are just working with, you have a set of many, say, firms producing something. Some firm has a profit, some defined profits more than that they have earned. Some have not earned more than that. Then there are some characteristics of the company or firm. Now, we can put the profit in a binary situation, whether the expectation is met or it is not met. If it is met, suppose we are taking that success has occurred. If it is not met, we can say that failure has occurred. And so the response, usually response are denoted by Y. So Y can take either a value 1 if success occurred, or a value 0 if success has not occurred. And then you have explanatory variables like the firm strength and say some commitment of workers and some those characteristics you can take. Then you can make a regression analysis between profit and the explanatory variables. And easily this can be explained. So these are new methods which can be done using logistic method, logistic regression method. So similarly, if you have a response, nominal response with more than 2 categories. Nominal means those orders you can order the levels, different levels, like good, very good, excellent. So these categories you can put the values, but you can order them in some sense. And explanatory variables are nominal. Then you have contingency table methods. Again, this is new. This is not an old method. This is a new method. For regression analysis also we are doing here. Then if it is nominal, more than 2 categories, response and categorical or continuous explanatory variable, then you have nominal logistic regression. Response is ordinal, explanatory is categorical and continuous, then you have this ordinal logistic regression. Now there are differences, and these are I think these are yet to come in your master's level syllabus. In case response is count, and then explanatory variables are categorical, then you have log linear models. Response is count and explanatory variables are categorical and continuous. Then you have Poisson regression models. So almost everything what is written in this slide is very new, of new nature, in the sense that they have emerged during last 30 years. Why? Because if you recall, the way you are implementing the simple linear regression, you can use simple calculator to find out the results. But in these methods, those simple calculation doesn't work. Means, let me take it, speak in technical terms. In simple linear regression, we are using ordinary least square method. But those ordinary least square methods are not applicable for this slide. Whatever is written here, all the methods, you cannot handle it using least square method. So you have to go in some sense the maximum likelihood, and the maximum likelihood also, the analytical the solution are very difficult to obtain for these methods. So you have to resort to some kind of numerical methods. And those numerical methods, again, implementation is a problem because they are iterative in nature. And you have to use some computer program, some computer software. I think you must have heard of the language R language, computer language R. And I'll recommend to all of you, you just have some idea of R, download it, it is free, and you can use it, and whatever is available in any other software, you can do using R, and it is valid. You don't require any additional license for that. You can simply download and start working with that. So all these methods can be implemented using R. Counterpart of R, which is, say, commercially available, that is called S or S+. These languages are there. But I'll recommend R for you, all of you. If you can learn, if you have to do statistics and some empirical studies, R is much better. Now, sorry. My talk was on statistical modeling to some extent. In very brief, I'll try to give you idea because this it's difficult in the time period 1 hour, 2 hours, it cannot be given. But I just try to make you familiar with all those new terms, what are emerging and what has emerged recently. I'll start from this statistical modeling. This is again a new term that we are using. Here what happens, we have variables, response and the explanatory variables. Response, usually one response only we are working. So it's in the equation form we are writing. I think you are familiar with this equation, what is written here, y is equal to alpha plus beta x plus epsilon. And this type of modeling equation we are using to model simple linear regression equation. So we have this type of equation. One is response, one side is explanatory variable with some error, and then we have a probability distribution for response. Now the thing is here, if you see this modeling equation, in the regression model, we have an assumption for this epsilon that they have a distribution, probability distribution. Usually, we take normal distribution for this with a zero mean and a fixed variance. This part, alpha plus beta x, alpha and beta are parameters, and alpha plus beta x is assumed to be known without any error. You can measure it. So this part is fixed. Epsilon is random. And because right-hand side, we have a fixed part and a random part, that's why y becomes random. So y has also a probability distribution. So when we have this type of situation, then we are in statistical modeling framework. Now, what are the things that we do with this in statistical modeling? So first, judiciously, we have to settle down with a valid or acceptable modeling equation like this. And then we have to estimate the unknown parameters because alpha and beta are usually not known. So we need to estimate, and there are several methods of estimation. Then once we have estimated the model, then we have to go for goodness of fit checking for the model. So this will show whatever you have fitted the model, whether it is explaining your data set or not. And then we construct a confidence interval over our estimated values for the unknown parameters. And we can perform testing of hypothesis. So this much we do in statistical modeling framework. Now, every step is important, and every step is very, very much, say, elaborate. So there are many methods depending upon what type of data you are handling. Here only also what you understand that this y is your response. Now, if this y is continuous, then you can use this normal distribution here for error. Because if it is not continuous, if it is discrete, then this equation becomes invalid. It is discrete, and if you are assuming that epsilon has a normal distribution, so that will not suit this equation. Why? Because left hand side is discrete and right hand side is continuous. This cannot be equated. So if your response is discrete, like I have just told you, that if it is a nominal scale or ordinal scale, or it is a count, then this modeling equation will not work with that kind of type of data. And we have say developed the regression models for those type of data where this response is discrete. Thirdly,
Oh my goodness.
yeah. So, okay, so this is there. I think they are not very serious, the participants. Unless they will listen to carefully, they'll not be able to ask me questions after this discussion, and they'll learn something, because what I'll be telling you simply in one book or two books you are not going to get. Anyway, so I'll speak on not much for this because you are quite familiar with this. Now, the models that I'm going to just give you a glimpse of. Linear model. What you have seen, I've told you that regression model is also a part of a linear model. I'll elaborate a little bit more. So there are linear models for handling the regression kind of situation. There are general linear models. There are generalized linear models. There are linear mixed models. There are generalized linear mixed models. Now, I think generally up to general linear model, you'll find this was prior to 50s, 70s also. But these three are very new. They started developing from 1970s, and now 2000, this millennium, you see, very active research has been taken place. You just search anything, the modern research in good journals, these will be the approach what has been used. So I'll just talk a little bit on these models. So first of all, this one, the linear model. Now, the regression that you have studied, simple linear regression, that is a part, or multiple linear regression, it is also a part of linear model. Now we know that linear model, it includes three types of things, which earlier people were studying separately. One is linear regression, another is analysis of variance, and the third is analysis of covariance. I have in previous slide, I have already shown you that when you're using analysis of variance and analysis of covariance. Now, the modeling equation is like this. Y is your response, X is explanatory variable, beta unknown constant vector, epsilon error vector. So these are written here. Though it is not mandatory to assume normality for epsilon, but if you do not assume normality, then you will not be able to get any confidence interval for the estimators. So you will not know whether it is meaningful or not. So that is why it becomes important. Otherwise, also estimation is valid. So usually we take normal distribution. Now, this normal assumption restricts you that this Y has to be continuous measure, or some sense it can be normally distributed. Okay, each of the Yi's. So this now here, what is written here, that it is normal distribution epsilon with zero mean. This is a vector, and sigma square I. I is a matrix. Sigma square is a fixed constant variance. And so what is written here is that each of these terms, like here, there are several equations. If you have n observations, so these are n equations written here, y1, y2, yn. Likewise, x beta is a matrix, epsilon 1, epsilon 2, epsilon n. Now, when you're putting this assumption for epsilon, it means that all the variances, variances are constant, as well as the covariances are zero, because this is identity matrix. So here the terms y1 and y2, they are uncorrelated. Epsilon 1, epsilon 2 are uncorrelated. So these are the conditions that you require for simple linear regression or linear regression, or ANOVA, analysis variance, or analysis of covariance. Now, the same equation can also be written as in the conditional framework like this. In books, you may find that y is equal to x beta plus epsilon with these This is one way of writing, or you can write it like this, that conditional expectation. I think these notations who have some training of statistics, they will understand that y given x is equal to x beta. So these both the things are same. Okay, notation wise they are same. And we assume that these are normally distributed with mean x beta and some variance sigma squared. So this is simultaneous approach of writing regression model. This is conditional approach of writing regression model. Both lead to the same results and same conclusions. So both ways books are defining regression model. Now, what is the difference? Why we are putting this in conditional format is that when we are going out of this normality framework, means when we are working with, say, binomial data or Poisson data, means count data or discrete data, then this assumption of normality is not valid. But in some sense, this can be assumed to follow this conditional y given x is equal to x can be assumed to follow binomial distribution or Poisson distribution or log normal distribution or Weibull distribution. So this can be extended. And you will see that these the extensions are called generalized linear models. So just in a little while. Okay. Now, but before that, I have to tell you one thing. Regression models you have run, and I think most of you must have seen this also. Are you familiar with Enscombe's data set? Anyone? Anyone will say something? Have you heard of Enscombe's data set? No, no one is interacting. Okay, so this is this scatter plot of Enscombe's data set. Very interesting. You can Google search and it would immediately come. And it's very famous, very popular also. And it gives you an idea. So how you can get wrong or wrong results you can get. Now, Enscombe has given 4 data sets. You can see 1, 2, 3, 4. Here I have not presented or I have not shown you, I'm not showing you the data set, but there are 11, 12 values. Scatter plot only I'm showing. You can see that the scatter plots are very different, isn't it? So this scatter plot seems almost random. About this line. Here you see there's a very nice curvilinear relationship. In this data set, it is almost linear and only one outlier is there, some outlier very far away value. This data set is almost vertical, again another outlier. So these are the 4 different scatter plots of the data set, 4 different data set, which Enscombe has proposed long back. Okay. But the very interesting thing is that if without noting this behavior, if you fit a regression model, simple linear regression model, y is equal to alpha plus beta x plus epsilon, then they give same result. Like for all the data sets, all the 4 data sets that I have just shown you, mean of x, you just notice x is here, this side on the x-axis and y is on the y-axis. So there are 2 variables. This is bivariate, all of this. Now in all the cases, mean of x is 9, mean of y is 7.50, variance of x is means sample variance is 11, sample variance of y is 4.125, correlation between x and y is 0.816 for all the 4 data sets. Linear regression for all the 4 data sets is y is equal to 3 plus 0.50x. And coefficient of determination of the linear regression is r square 0.67. Now, if you just see this, the results for regression model, the correlation between x and y, the coefficient of determination for all these 4 data sets are same. But which data set do you think that the regression model is applicable? The regression model is applicable only for this data set, the first one. Top corner, what you can see. This is the only data set where you can or you are allowed to use regression model. If without noting the nature of the data set, you are using regression model, of course you will get the results, but the results will not be interpretable and very wrong type of inference you may get using those results. So these 3 data sets, those models or the regression model is not valid. That is valid only for this. So you see here also, there are several possible situations, and everywhere just blindly you are not supposed to perform linear regression. Linear regression is not valid for this data, not valid for this data, not valid for this data. So you have to be careful when you are using regression models. So this is with respect to that. Now I'm just coming to the new developments. What is general linear model? Any questions up till if anybody wants to ask anything? Yeah. I hope that they are listening.
Yes, they are listening.
So any question? Nobody?
Hello, sir.
Yes, tell me.
So one question. Sorry, I could not turn on my camera. One question, sir.
Yes.
There is, you've mentioned R statistical package, right, sir?
Yes.
Yeah. So SPSS is we've all known the most I mean common statistical software,
Yes.
which is a paid software.
Yeah.
Right. So R is free. It's like an open software.
Yes.
So why is it not familiarized by researchers? Or I mean, when research is introduced, I mean the analytical part, everybody suggests SPSS. R can even R can be is capable of doing exact like analytical tools. It has all the framework, all those things like SPSS. So why R is not familiarized, sir?
R should be, because R has some problems when you are writing any program. If anything is wrong, it doesn't give you any suggestion. Okay. So you have to be familiar with that before using. And SPSS, what happens here? It is you just push a button and you are getting the whole result. This facility is not available in R. Plus, why I'm telling R? SPSS, what previously we have discussed, we can use SPSS. But beyond this slide, whatever you see, it is yet to come in SPSS. It is not. Got it? There are so many conditions that only R can handle. These situations beyond this slide, I think I have 20 slides, not much.
All right.
But this, okay. See, then we'll discuss it now. So first generalization of linear model was in the name of general linear model. That in econometrics you must be finding this. But this is not very popular in sciences because of some regions, but there are some situations where it is popular. I've just talked to you. The difference is modeling equation is same, y is equal to x beta plus epsilon. Other things are same, but only change is here. The epsilon here now is a random error vector, usually assumed to follow normal 0 with a variance covariance matrix, which has non-zero elements, of diagonal elements also, and even the diagonal elements can be different. Means it can model heteroscedastic situation, and you must have used something weighted least square or those type of methods which are being used when you have different variances. Different error means heteroscedastic situation, but say the covariance is usually a 0 there. But if covariances are non-zero, then of course theoretically you're writing, but practically it is very difficult to implement. Why? Like suppose you have 10 observations, 10 y1, y2, y10 up to y10, then the off diagonal elements will be 45 different values. Diagonal elements are, if they are also different, then there are 10, so 55. Then you have betas. Betas means then you have, suppose you have 5 betas. So 45 plus 10, 55 plus 5, 60. Now you have 60 unknown parameters and you have only 10 observations. You cannot estimate the parameters. So it was found that, it was realized that we cannot keep many of the elements of epsilon as unspecified. They have to be some condition imposed on the covariance structure. And we are doing this. There are certain situations which you do with covariances all 0 and variances different. You have a weighted least square kind of application are there. for heterogeneity, the modeling heterogeneity. But now if you are putting covariances, then we put some special structure to the covariance so that your number of unknown parameters is well within the number of observations so that you are able to estimate it. The applications are like it is applied in heterostatic structure and geospatial modeling, kriging. If you have heard anywhere that geospatial modeling, it looks like this after you do regression and you plot results, it will give you plotting like this. This is more applicable in geology, geography, or to some sense in disease mapping also. So here you see the sigma has been put as sigma square epsilon of Dij by D some I. So instead of 55 unknown parameters, now with this specification, you have the parameters unknown, only sigma square is 1 and phi is the other. What is Dij? Dij is the distance between 2 points. So from 55, you have reduced the number of parameters to 1. This is only one specific exponential model that I'm giving you. I'm just showing you. So there are 2 parameters, and those betas are, suppose if there are 5, then 5 plus 2, 7 parameters, and you have n 10. I have taken started with in the discussion last slide. So 10 plus 2 means 12. Sorry, no. 7 parameters, unknown parameters, and 10 observations. So you can estimate it. So this can be implemented like this. This is also a new modern method, and in geology, geography, etc., you will find this. This is called geostatistical mapping, okay, or geostatistical regression analysis. Now I'm coming to another point. Another development that is taking place is generalized linear model. Previously, I have just talked about the general linear model. Now it is generalized linear model. Both are entirely different. In generalized linear model, we handle response that have distribution from one parameter exponential family of distributions. We have a family of distributions we define, which is called exponential family, where the terms are nicely can be put in as exponential form. So anyway, the distributions, the basic distributions that you have heard, like Bernoulli distribution or binomial distribution or Poisson distribution, log number with one parameter known, Weibull with one parameter known kind of thing. This all are one parameter family only we are thinking of, we are talking of. So all these belong to, including normal with sigma square known, all these belong to exponential one parameter exponential family, and you can perform regression with all these. Now, previously, what we are studying or what is in your syllabus up to what you will be studying, that only takes normal distribution. But now the regression models are extended beyond normal to take these distributions also. Bernoulli, binomial, Poisson, log normal, Weibull, these regressions you can do. And if you just Google search, you'll find many research papers which will be very new publications, say, or most of them will be from 2000 onwards only. Now, these models, least square method doesn't work. You have to somehow enter into maximum likelihood paradigm. And if you'll be interested later on, sometimes if you're reading, then you'll find that there are so many types of maximum likelihoods, like marginal maximum likelihood, quasi maximum likelihood, conditional maximum likelihood, there are several maximum likelihoods. Now, these models again analytically cannot be implemented. You have to implement it using some computer software. Again, I'm repeating R. R is free software. S plus is its commercial version. These are new in SPSS type softwares. It is yet to come. That will be very expensive. Plus, I do not know what the limitations, the conditional where they'll be putting. In R, say linear model means regression analysis, you can fit in a very small command, lm, y, then this x. This much will fit your regression model. So like this, here also GLM and other type of some commands are there, which this can be fitted. But right now, I'm not interested in those fitting how to implement it. I'm just trying to make you understand that regression models have gone much beyond this normality as an assumption. You can do regression with many different types of variables. Different type means they are different with respect to the measurement scale. So this is generalized linear model. Then, but here slightly different. If you remember, The linear model, there we were telling that expected yi given x beta, where g was not there. Now here in generalized linear model, while developing this, I'm not giving you mathematical notations here just to make you afraid, because they are quite complicated. I'm just for application point of view, I'm writing this. Here, what do we model? We model this g is a continuous invertible function, a monotone function. This function of this expected value of y means mean of yi. A function of mean of yi is equated with this linear component x beta. This regression where beta are regression coefficients. So here the idea is a little bit different. And then we have methods to implement generalized linear models here. Like you see, if you are dealing with a Poisson distribution, then this g becomes a logarithmic function. If you are dealing with binary, then this g becomes a logic function. So this g has some value, and then we are implementing regression also. These are called generalized linear models. These are very popular these days and very effective, and a lot of applications in many areas there, including econometrics. Now, I'm coming to another point that previously the model that I've just shown you, that epsilon in linear model, epsilon, we take an assumption that epsilon is normally distributed with mean 0 and variance sigma square I. I is an identity matrix, so the off-diagonal elements are 0, means there is no correlation. Means those were valid for uncorrelated data. Now, once we have a correlated data, then what we do? Like you see, correlated data can be in the form of cluster data or longitudinal data. Like suppose if you're talking of production and your response is production of some food grain in Mizoram for 10 years. So in Mizoram for 10 years, there are several types of or several categories of food grains can be. Like suppose some say rice or say pulses. You make different categories. So now your Y, the response will be pulse rice measurements, then the measurements on pulses, then measurements of some other things, say vegetables, and for 10 years. Each one suppose for 10 years. So you have observations will be writing as Yij, where I will represent the type of this rice or pulses or vegetables, and then how many observations are there. So this is the example of clustered data, or this is longitudinal data. You can regress it. In this regression, you will be able to, because this data will not be independent. They are independent between, but they are dependent within. So this type of data also can be modeled, and this type of data can be regressed. The model here now becomes expected value of Yij, which just now I told you that ith category, jth value or observation, and beta k. But you see, here if you consider the entire vector y, then it will follow a multivariate normal distribution with mean x beta, and V is your variance covariance matrix. Now this V is a huge matrix. Now suppose if you have 10 data points, then the dimension of this V is 100 by 100. Again, I'm repeating, if you have only 10 observations altogether, 10 say categories, then this will be, and each one has 10 observations, then this V matrix has dimension 100 by 100. So just imagine such a huge matrix, how to handle, but we have computer programs and we can handle those matrices. Now this V is a diagonal matrix. Diagonal means V1 is another n by n matrix. This is also n by n matrix. All are n by n matrix in the principal diagonal, and all the off diagonal elements are 0. So this is a huge matrix, but with this huge matrix, you can have some idea of the correlation also. Intra-class correlation usually will work, and this is the dependent data, but we have regression analysis for dependent data, which goes in the name of clustered longitudinal data. Slightly the same data, clustered data or correlated data, if you are putting in a different framework, in the hierarchical model framework, Then it is called multi-level model. It is almost similar. It also handles the same thing. It also does the same thing what the previous slide is doing. But here you will be more interested in assessing this interclass correlation. Here also, I'll be telling you that suppose this model I'm writing here, that Yij is equal to mu plus alpha I plus epsilon Ij, where this alpha I is a random here. It is not fixed. It is random. Mu is fixed. Epsilon Ij is random. So this is a mixed model, linear mixed model. If you remember previously, I have just written the name general linear mixed model. So this is an example of general linear mixed model where we have a random coefficient here, another random coefficient, AI, which represents the ith class or ith category. So we have methods to handle this, again, computer software. But what I'm trying to say that most of the works today, these days, where we are developing or applying, we are doing with clustered data. And these are the examples of clustered data. These are new things, new materials. If you are interested in any portion, you can always search and you can have some idea. Now, anything up to this point? Anyone, if you want to ask anything?
Sir, if you, sir, one question. If you can demonstrate it with the application, it will be more, what to say, easy to grab. I think it's quite tough for the UG students, I think.
Actually, you see, the application, if I'll be going to give you, that will take another 2-3 hours.
Okay.
So for today's talk, I'm just making you understand these things. Okay, these are the new things that you can think of in
Yes,
future.
it's very informative, sir. It's very informative. Yeah.
Just for information, because many new developments has taken place, which I think that is yet to come into our academia, and particularly in the region what we are working, we have tough and now the accessibility availability is there. But so these are the new things that you can think of. If you'll be interested, you can search it and you will get much of the material. Okay.
Thank you, sir.
And if need be, then we can think of having another talk. So now I'm taking you to a very new area, which is very recently it has been popularized, though it has proposed long back, it was visualized, but the applications are only of 2000. This area goes in the name of spatial econometrics. Got it? Have you heard this name, spatial econometrics? Now,
No, sir.
Yeah.
No, we never know the name earlier.
Okay, just let me introduce you. Spatial, you see the spelling as space, it relates to space, two-dimensional space or land area. Now, this I have taken only from this Wikipedia, which everybody can get. I'm not going into any technicalities. Just from Wikipedia, I have taken this definition. I'll read it out once for you. You can also read here that spatial econometrics is the field where spatial analysis and econometrics intersect. The term spatial econometrics was introduced for the first time by the Belgian economist Jean Pelink. Okay, and in the general address he delivered to the annual meeting of the Dutch Statistical Association, May 1974. In general, econometrics differs from other branches of statistics in focusing on the theoretical models whose parameters are estimated using regression analysis. Spatial econometrics is a refinement of this, where either the theoretical model involves interactions between different entities or the data observations are not truly independent. Thus, models incorporating spatial autocorrelation or neighborhood effects can be estimated using spatial econometric methods. Okay, such models are common in regional science, real estate economics, education, economics, housing market, and many other. From Wikipedia, throw a pani dena. Okay, from Wikipedia, I've just taken. I'll just try to just try to bring you into this topic, this area. You see two terms here you have heard. One is we are talking of spatial data, means the data which occurs in space. So the Mizoram is also a space. If you just divide it into different district boundaries, you will get something like a lattice structure. And suppose you are talking of employment rate. So this is one lattice, one area, another third, fourth, fifth, like this. So there will be several areas there. And if you talk of say employment rate, then you will be getting the employment rate value for each of these areas. Now, we have three types of spatial data, but this I'm talking only of the lattice data or aerial data. This type of structure is called a lattice. With every lattice data, we firstly make a neighborhood matrix so that this can be made connected. Now, there are several types of neighborhood matrix. I'm only writing here the neighborhood matrix, which is a contiguity matrix, it is called, means if these two share a boundary, then we will write 1. If these two doesn't share, like 1 and 6 doesn't share any boundary, we'll be writing 0. And each one will not be assumed to share its boundary with itself. So the diagonal elements will all be 0. So just for the first one, first row, this is the first element or first cell. It shares a boundary with 2, that's why 1, 2 is 1. It it doesn't share any boundary with 3, so that's why 1, 3 is 0. Shares a boundary with 4, so it is 1. Shares a boundary with 5, so it is 1. Doesn't share boundary with 6, so it is 0. Doesn't share, so it is 0. So like that, each one you can make. So implementation of spatial econometrics goes via this line. You have a lattice structure. You have some measurement here in each cell of lattice, and then you have to construct a neighborhood matrix. There can be several neighborhood matrices. This is the most popular one, contiguity neighborhood matrix, we call it. Okay, and then we analyze, we do regression analysis. I'll show you the model later on. But do the regression analysis, and after doing regression analysis, we present the say results. Regression estimates expected values on the map. I'll just show you what we have done here for stillbirth rate for India. So for the final result will come something like this. Got it? You have to geographical area. These are district level values of stillbirth rate. And then after the analysis, the expected values are being presented like this. So this is one advantage, that immediately it is very eye-catching, new. Here you are using some more applications. You are doing regression and then you are presenting data like this. Here, of course, from this you can identify what are the colors, what is the number for stillbirth rate has been given. So these here in this region, stillbirth rates are very high. Similar thing can be done with using employment rates for district level data, and you can present this. So immediately ready-made, you can get it. Now I'll just show you the models. These for special econometrics, the models which is being used are in the form of auto-regressive models. Now, auto-regressive models is first if you have done time series or you have read time series. This type of terms are there for time series, and this is an extension of time series in the sense that here you have dependence in all the direction. In time series, you have dependence in an order. Previous value is related to the next value kind of thing. So there is an order. Here we don't have any order. And this model can be written like this: I minus b, y minus x beta is equal to epsilon. You see, epsilon is normal 0 sigma. Usually the sigma is taken as what is you are taking in linear model. Sigma square I means I is again a entity matrix of diagonal 0. Here what is happening, you see, I'll just try to make it clear that previously in general linear model, where I have shown you that geospatial modeling are done. So there the variance means the dependent structure we are putting in the variance covariance matrix of epsilon. But for spatial econometrics, the dependent structure is put in the mean structure of y. This is what is the difference. Dependence can be put either in mean structure or in the variance covariance structure. For geospatial modeling, we are putting it in the variance covariance matrix of epsilon. But for autoregressive models or for this econometrics, spatial econometrics, we are putting dependence here in the mean structure. So this is SEM, actually spatial error model. I'm not written it. But you see, usually what happens that this B, what is written here, is rho sigma, I think somewhere it must be written. B is equal to rho W. Now what is W? W is this. This matrix is called W. And then B is rho W. Rho is a spatial association parameter. So just if you bring it here, then it will become I minus rho W, Y minus X beta. You know what is Y, what is X beta is equal to epsilon. So this is what is the model. And this matrix multiplies. So what it does, it takes care, because in W you have seen that if there are intermediate neighbors, then only the value is 1. So once you multiply it, all the values which are in the neighbor, that is only coming, others are 0. So this regression model is like this. Now I'm not be elaborating because just now I heard that somebody was telling the graduate students, na? So I expected all research for PhDs or this teachers. So I'll not elaborate much, but I'll just tell you that there are autoregressive models. This is with a special notation that we are using here. It is written here. There are two types, basic types. One is simultaneous, one is conditional. Now, again, because I've told you in general linear model, simple linear model, that the conditional as well as the simultaneous both give rise to the same analysis and results. But here in spatial, what happens? Oh, sorry, this happens also in time series. But in spatial, they are different. So we have two different modeling approaches here. One is called simultaneous autoregressive model. Another is called conditional autoregressive model. The analysis, the results, the interpretations are different for these. In spatial econometrics, they are only concentrating on this simultaneous model. And they are generalizing this simultaneous model. Now you see, in the simultaneous autoregressive model here, what are you doing? That a present value can be dependent on the previous one. The observations, or it can be the present error can be dependent on the neighboring errors. So when we are putting it, that model I have not written here, but then it is called spatial moving average model. This is called SEM. Actually here Y minus X beta is there. So this is error, another type of error. So this is SEM. There are no, these are the work of the hour just for 2015, 20, 21. If you are search, you will get the research papers from econometrics. What is coming will be in this line. These are being extended these days, and there are two different types of models here. You see, this is with respect to data. This is with respect to error. So these type of models are known in the name of SARAR 1-1. Because only first order is being considered. This can be elaborated to higher orders, second order, third order, fourth order. And this is what the research going on in case of spatial econometrics these days in India and world over. Got it? So now my request for the researchers will be that if you can enter into this area, or whatever I have told you, anyone like a generalized linear model, or even general linear mixed model, or generalized linear mixed model. Well, generalized linear mixed model is a counterpart of general linear mixed model for non-normal data. So that slide I have not kept here. That becomes much more complicated technically. So, or this spatial econometrics, which is an emerging and very new method. So here, if you can enter, these are very, very new, and I'd like you to enter in some of these areas so that you will also be modern in your tools and techniques. That's all. That much only. No.
Okay, sir. Thank you, Dr. Jha. That was a very intricate yet interesting and enlightening lecture on statistical methods and study, which should prove very helpful for ongoing researchers and emerging scholars. And we shall go ahead and take some time for questions now.
Yes.
And just a reminder, please be sure to type your questions into the question box or the chat box. or otherwise the participants can unmute themselves and ask questions as you like.
Yes, directly they can interact, no problem. Yeah.
Okay.
Sir, it's not a question. Can you put the references of your this presentation of the references? Yeah, references.
References like, okay,
Oh,
these are
books
the
and all
terms,
books or economics books that you have used for your presentation.
Oh, there are several books, there are several
Okay.
write-ups, there are several research papers. Most of the things that I'll be talking or I have talked, okay, very few, like Enselin's book is there. One Enselin, you can write this name.
Enselin.
Pleasant and Prucha. There are several authors who have their books and research papers. Most of the things are in research papers now. It is yet to come in the form of books. But some new books are coming. Even 2021, I have seen a very good book. I'm missing the name. You can Google search because these days we don't have that much restriction. The Google search, you'll find plenty of.
Thank you very much, sir.
Okay, welcome.
So there are questions on the chat box. Can you see them or should I read them out for you?
You just read it out.
Okay. The first question is from Dr. Lelzu Iliana, and he is asking, when talking about demand as a function of price, where demand is a dependent variable and price is an independent variable, is there any case that independent variable can change without changing independent variable?
Well, you see. These are very specific problems, and desto better if you can ask your teacher or interact there, what specific problem you are thinking of. There is a general definition for dependent and independent variable. Dependent variable as those on which you are interested in doing something or finding something and doing some analysis. Independent are those which you cannot control. Got it? You don't have any control on that. It comes and that affects that should be affecting your response. So in what you are interested, sometimes or many times also it is possible that when both are, there is an interdependence and it's very difficult to make one independent and one dependent. So it will depend upon the context that what is your objective on which you want some analysis to be done and some results to be predicted. So sometimes it becomes very subjective also, because for this particular situation, this is independent and this is dependent. So that way, so the general thing cannot be said, depends upon your objective and what you're interested in. Yeah, next.
Thank you, sir. So there is another question from Mr. Samuel. I shall read this out loud. Economists mainly work with time series data set, and that most of them happen to be trending series. If such is the case, most often than not, unfortunately, they happen to be non-stationary. Even when they are non-stationary and are at least integrated of the same order and also co-integrated, modeling their relationship is not such a problem. So my question now is, what is the trending time series? What if the trending time series are non-stationary and are also integrated of different orders? Say one and two. Am I reading this correctly? What modeling do you suggest for finding a relationship between such trending time series?
Okay, the thing is that the spatial models, when I was discussing, spatial model is in a higher dimension of dependence. Time series in one direction. In spatial, you have all direction dependence, isn't it? You cannot fix the order. So this is first, this is second, this is third. Time series models have started developing much earlier. Initially, we didn't have many of the tools available for analysis. So those days we were mostly concentrating in getting in stationary time series, and then because we could develop only analytically the solution for that. But nowadays, these are not any hindrance. If you just search, you'll find that even in different situations, you can have methods where you can get analysis and you can get a valid result, which you can interpret. So come out of those and go to the new tools. Like you see, I've just shown you that in case of this matrix, where it was that, this neighborhood matrix. Now, if you are dealing with the time series data, which has a linear this dependence, you can make a neighborhood matrix, and the same tools can be used, what is written here, to analyze time series data. Okay. So now it depends upon which perspective you are talking of. If you are talking in the perspective of the classical time series models, then things are a little different. But if you are talking in terms of modern time series methods, then things are different. And you'll find that many of the limitations, what was there in the classical analysis of time series data, has been done away with in your modern approach. So I think you read something a little bit more, and you will get some better and up-to-date analysis and answers. Yeah. Next one.
I have a question myself.
Yeah.
To control the effect of continuous variables, right? Is it better to include it as a random variable or a fixed variable?
Well, again, the same answer or similar answer. Fixed or random. This is contextual. What you are doing, what is your objective, whatever data, or what you are ready to think. Like you see, if you have some data, some observations with respect to temperature, suppose. Got it? So temperature you cannot control, so that you have to take as fixed. But suppose if you want to study something, what is the productivity, okay, of something with respect to some different levels of fertilizer. Now, if you are interested only 3 levels of fertilizer, say per hectare this much 10 kg or per hectare 20 kg 30. If only you are interested in 3, then it will be a fixed model. But if not, there are only not 3 levels, but you are trying to predict or talk in the entire range, then it will be a random. You have to take it as random. Now, what is the difference? In the fixed parameters, if you are keeping, then you can estimate it. Got it? You can find out a confidence interval. But if you are taking it as a random, then you will not be able to estimate it. What you will be estimating when it is a random component, your assumption is that it is normally distributed, normally distributed with mean 0 and variance sigma square or something else, tau square. Now, so any random component, this is also called latent variable, and latent variable doesn't have any magnitude. It has only a variability. Got it? So if you are putting a random component, it will contribute only in the variance. It can reduce the variance. Now, reduction of variance means what? In analysis of variance table, you must have seen that, like the treatment sum of squares divided by error sum of squares for significance. Got it? So if error sum squares become larger, you may get a significant result. But it may be possible that there are some assignable causes which you have not considered and which are included in the error. So one possibility is that you bring in a random coefficient, or you bringing in this latent variable. So that will be having some variance, and that variance you can extract from this, and the significance may go. But this is second one. If you are taking out some variability, which can be predicted, then your confidence level increases. Got it? So just try to understand this. If this coefficient is fixed, it will contribute into the mean. If it is random, that will contribute into the variance, not mean. So this is what is the difference. Now it depends on the context where in what we are interested. Got it? A particular variable can be taken fixed in one situation, can be taken as random in another situation. So it varies with situation. There is no point fast. Yeah, anything else?
Okay, sir. Thank you so much.
Mm-hmm.
Is there any more questions from the participants?
Yeah.
Some question you'd like to ask?
No one.
Okay, sir, I don't think there is any more questions.
Okay.
So it looks like we have covered all our questions. And so to wrap up our session, we shall now call upon Mrs. Lerwin Philly. Miss Lerwin
Kim
Philly.
Kim, Miss Kim Kim,
Okay.
there is one question in the chat box.
Oh,
There
okay,
is one
sir.
question from the chat box from somewhere.
Okay, so there's another question that just came in. Sir, I shall read this out loud. What is so special and unique about special econometrics? Can you illustrate its popular application for research?
Yeah, there's a new area that has emerged very recently. Though the term was coined in 1974, as I've shown you, but the analysis of very recent origin. Now, there can be some discussion, but I'll just suggest you that you Google search spatial econometrics and see the amount of literature that will come there. You go through that, and you will find some very interesting application. And this is very modern now. What is happening is that why we are doing statistics, you see. The basic thing for which we are doing statistics is that we are able to measure the uncertainty in terms of variance, particularly what we are doing. Like you say, I'll give you an example. Say palmist, if you think of a palmist, suppose who sees my palm and just gives me that, okay, my lifespan is 100 years. But the problem is that there is no confidence interval on this statement. So this statement is not scientifically valid. Okay, you may believe it in this, but it is not scientifically valid. What we do, we also put or can predict something like this. But when statistician will be, or through statistics, if you will be predicting, then you will be able to construct a confidence interval. And that then it becomes scientifically valid. So basically, you are able to measure the uncertainty and then you take decisions. Now, in spatial model, what happens? If there is some variability due to space, spatial difference, you see the conditions of Saiha district and the condition of Aizawl district, don't you find they are very much different? So if they are different, then this geographical location has also some effect on productivity or employment rate or any other things that you can think of. Now, if you are bringing in this disparity also into your model, means you will be knowing more about your data set. So that's how it's developing. So in that sense, only the spatial is also applicable.
Okay, sir. Thank you. I hope the answer is clear. And then is there any more question? A few minutes can be spared if there is any more question. Okay, we shall go to the next segment of our webinar. To wrap up our session, we shall call upon Ms. Lerwin Philly, Associate Professor, Department of Economics, who is also the Secretary of Research and Consultancy Committee, Govt Thankima College, to deliver vote of thanks.
Good evening, everyone. It is a great honor to propose the vote of thanks to all who have helped us in making this webinar a very resounding success. First of all, I would like to give my hearty vote of thanks to our speaker, Dr. Aizawl, for making an excellent presentation and making this webinar a meaningful one. I would like to express my deep gratitude to Professor J.V. Nuntunga, Principal, Govt Thankima College, for taking initiatives in bringing this webinar to a success. I also thank all the faculty members of Economic Department for their overwhelmingly role in making the event success. I would like to thank all the wonderful participants for your time and cooperation. And finally, I thank all the students of Govt Thankima College and all the members of Research and Consultancy Committee for your cordial cooperation. Thank you and good night, everyone.
Thank you and good night.
Good night, sir.
Okay. Bye.
Good night, sir. Thank you.
Good night, everyone.
Good night, Jivi.
Good night, everyone.
Good night, sir.